Okay, well, hello everybody, and you're all very, very welcome to our info session to the MSc in Subsurface Characterization and Geomodeling. My name is Anthea Lakia, and I work for the UCD School of Earth Sciences. And we also have Professor Tom Manzocchi here with us. Do you want to introduce yourself there?
Yes, okay, yeah, I'm one of the associate professors in the School of Earth Sciences, and I guess I've worked quite closely with course director Peter Horton in setting up the scope of this MSc. So I'm here to answer questions, and I'll give a bit of an overview really on where we're coming from with this MSc.
Brilliant. Oh, thank you, Tom. And I guess today the structure of this session is that we'll hear a little bit about the course from Tom, and then after that there'll be an opportunity to ask questions. And so I'm going to hand over to Tom to talk to us about the Masters and give us an introduction to it.
Thanks, Antea. Yes, okay. So I'll give a bit of an overview really on what our MSc is all about. So as I said, my name is Tom Manzocchi. I'm part of the team who will be teaching on the MSc course. I'm also part of the team that really came up with the concept for it. So what I thought I'd do in this presentation really is give you a bit of a background about where I come from and what my sort of research interests are, and then focus in on how that fits in with our new MSc in subsurface characterization and geomodeling. So my background really is in the oil industry. That's where I started in my first job back in the 1990s, so quite a long time ago now. And really, I spent a few years working in the North Sea out of Aberdeen, and then I decided to start doing some research. So I stopped working in industry and started working as an academic, as a researcher, and then more recently as an academic. But I suppose, the 3 years I did spend in industry very much focused all of my subsequent research really towards very applied topics, usually related to the petroleum industry, but always really about modelling and about the representation of geology in subsurface models. So when I started working, back in the 1990s, really, the big technology that was happening at that time was logging well drilling and directional drilling. So this was absolutely fantastic technology that allowed you to drill holes, several kilometers into the subsurface, but have some recording tools that were directly behind the drill bit that would give you a real-time signal at the wellhead of some kind of electrical signal or radioactive signal of what was being drilled through. So this meant that rather than having to wait for the cuttings to circulate up to the top of a well, you could actually think in real time about the geology you were drilling through, and you could make real-time decisions about how you wanted your drilling to modify. Now this particular slide that I've shown is from about 2002, and this shows the next step of this, which was really associated with the technology that allowed communication from the wellhead, which might be in the middle of the North Sea or in the Gulf of Mexico or offshore Nigeria, from the wellhead to the office, where you could really start plugging this data into large computers that contain reservoir models that really allow you to modify the model in real time so you can make much more sophisticated decisions about where you're going. So it's really the advent of all these technologies together that have really allowed us to improve the way we drill into the subsurface. And nowadays, the downhole data acquisition, logging while drilling is really becoming, it's still evolving. It's always evolving. And some of these tools are incredibly sophisticated now and really allow you to modify the geomodel as you're drilling, so that you only need a really quite rough and ready, in some cases, drilling plan to start with, because you modify as you go along. So this is really seat of the pants geomodeling that influences drilling in real time. Of course, the other thing that's changed massively since the 1990s is seismic data. And 3D and 4D seismic data acquisition is really becoming much more sophisticated. It's improving our acquisition methods with bottom hole seabed seismic and various other technologies are always improving the data we acquire. So we get much better images of the subsurface. And if we've got 4D seismic, we can often get images of fluid movements and stress changes within the subseismic over the interval between the seismic acquisition as well. So as geologists, we're ever faced with more and better data. But of course, there's still a requirement to interpret. There's still things we can't see. So this particular seismic data set that we're looking at here from the Gulf of Mexico, for example, has some very nice, some very clear normal faults on it. And understanding the structure of normal faults has been one of my research topics in academia. So one of the things I research, for example, is how we can risk or how we can establish the risk that we might have communication across faults in subsurface models. So this example here, for example, on the left there, that purple horizon is a flow unit. It's about 10 meters thick. It could be a permeable sandstone aquifer for potable water. It could be an oil reservoir, as it is in this case. And what we're looking at there, the gaps between the purple horizon, of course, are faults, where it's been faulted. And based on the seismic interpretation, you can map those faults in 3 dimensions. But of course, seismic resolution is not perfect. And you can't see the details of what's going on close to the fault. You can see that 400-meter scale bar. That is pretty much as small as you can see in this particular seismic data. But when we look at the faults in detail, when we look at real faults, we know that there's a lot of structure, a lot of complexity in real geological faults at that sort of scale. So one key question, if you're managing an oil reservoir, a gas reservoir, a water aquifer, is to really understand what the communication across these faults might be. So on the right there, that image at the top shows that particular fault highlighted by the grey arrows on both sides of the fault, so the hanging wall towards us and the footwall in the back, with this 10-meter flow unit, and you can see there's no communication across that fault. But if we start building probabilistic models of what likely structure we might get below seismic resolution on that fault, we start getting potential models like the 2 below, and we can start risking communication across that fault. So what's the probability that actually that large flow unit in the middle of that model is in communication with some of the units on the far side? So risking what's in the subsurface is a really important part of prediction. Another research topic I work on is improving the representation of sedimentary systems in subsurface models. So these 3 models that we're looking at there, for example, are models of yellow sands, permeable porous sands, within a background of impermeable black shale. And these could represent reservoir sequences in many sedimentological settings. But the way we model these influences our predictions about the flow of fluids through these permeable systems. And there's really 2 extremes. You can model fantastic geological reality, or you can make models that are useful because you can tie them to well data. And it's really trying to improve the usefulness of realistic models, or the realism of useful models, that is one of the significant research themes that are going on in geomodeling at the moment worldwide. And we're doing research in that area as well. And in fact, this is our flyer, if you like. This is one of the images that we use a lot when we're talking about this MSc course. And what we're looking at there on the left, those yellow and grey units, are one of these geomodels that have come out of our research, where in this case we're really trying to understand and provide a way of modelling the stratigraphic sequences that we observe in the real outcrops on the right of this, which are deep water turbidite deposits from the west of Ireland, but they're a very close reservoir analogue for a lot of the reservoirs that we see in the Atlantic margins, for example, in the Gulf of Mexico or offshore West Africa. So really trying to understand how we improve representation of geology in subsurface models, I suppose, is a topic of my research. And as I said, this slide brings me, I suppose, back to talking about the MSc rather than talking about myself. But I think it's important that you appreciate when I go forward in my discussions of the MSc, that what I will be presenting, I suppose, is very much focused, given with my focus and my background. So I will be talking much more about the geomodeling side of things and the characterization side of things, for example. So, well, where does this MSc come from? Well, until quite recently, until about 4 years ago, 3-4 years ago, we were running an MSc in petroleum geoscience. And this is one of the graduating classes from that MSc. And, we were a relatively small MSc, so this is a class of about 16, I think. There's a few instructors in this photograph as well. And we stopped running that MSc because the oil industry hit a downturn, and it was very, very, very difficult for the students to find jobs in the hydrocarbons industry. In about 2019, I think, was the last year we ran this MSc. So, we were very happy with the sort of technical content of what we were teaching. We were happy with our teaching setup. We were happy with how we run our classes. We felt we had a good team of instructors together in the Earth Sciences School in UCD, but we needed to change the focus of what we were teaching, really. So that's why we came up with this idea of the MSc in subsurface characterization and geomodeling. I suppose this slide is summarizing some of the thinking that we went through when we were thinking about what to do. We recognize that employment opportunities for geoscientists are changing very, very quickly. And we also, of course, appreciated that things that had been normal in historical times, and here I've used the example of the Shell concept of the job for life. You join Shell at age 20 and, you've got a job for life, and they evolve you into a Shell person. That kind of employment model no longer existed, really. But despite that, we also recognise that the necessity to understand, model, visualise and make predictions about what's in the subsurface is not just specific to petroleum geoscience, it's across many different geoscience application areas. We also knew that, sophisticated tools for interpreting, analysing and modelling the subsurface didn't just develop in the oil industry, they developed simultaneously in many different industries, and are evolving very, very quickly in many different industries. But despite this rapid evolution, and despite the fact that different industries do things in different ways, we also recognise that many of the underlying principles behind these softwares and tools are basically very similar. And we realise that a generic understanding of the key methods behind these approaches, these tools, these technologies would really provide flexibility in pretty much any applied geoscience career path. So we took these ideas really and thought about what was a useful MSc, and that's why we came up with this MSc in subsurface characterization and geomodeling. We decided that the way we wanted to tackle this really was by focusing not so much on specific application areas, but by focusing on the principles that are common to those application areas. So what I've got on this slide really is a list of geoscience principles that we felt were important in subsurface characterization. For example, stratigraphic principles, structural geology principles, an understanding of hard rock geology, of quaternary geology, an understanding of how fluids and stresses influence and interact with this solid framework of the geology. So, we felt that by providing really firm background in these geoscience principles and then coupling them with the principles on the right there, the principles of geomodeling, that we would have an MSc product that was applicable and relevant to many application areas. So what I've got here really, these are pretty much the names of the modules in the course, split into these 4 sectors. So we're not assuming, I mean, obviously we're assuming that people taking this course are going to be geoscientists, principally with a geological background. So we're coming at this with as geologists rather than as geophysicists, for example. Although, of course, we are covering geophysics in the course as well, but we're expecting quite a significant background in geology before we, as a starting point, really. But then things like geomodeling, which is one of the central themes of the MSc, we're not expecting a background in geomodeling, and so the basic principles of geomodeling is one of the fundamental modules that we'll be dealing with at the beginning of the course. But then we're also going to look at how we manipulate the data that we need for geomodeling in the first place, including some sort of ideas about simple Python programming to do that. We're going to look at applications of geostatistics, how they fit into geomodeling, and a module on fractured rock modeling as well, because the way we treat fractured rock is very, very different to the way we treat sedimentary rock, for example. In terms of data, the data has to come from somewhere, so we're going to look at drilling, well logging, geophysical data acquisition, remote sensing methods, and we've also of course got modules in which we're applying this stuff. So we're looking at a module in applied geoscience, which is really where we do go through industries specifically. We've got a number of a sort of practical side to this course, 3D mapping and modeling using, some of the key softwares used in various industries, ArcGIS, Petrel, Leapfrog, for instance. There's individual modeling as well as team-based modeling exercises. And, a key part of the MSc is an individual applied research project. So, yeah, I mean, I put this slide up really to remind myself to say that although I'm coming from a background of petroleum geoscience, predominantly, we are a reasonably large school of earth sciences, and other instructors on the course have very different backgrounds. So this is just 2 examples of recent publications where they've used our geomodels on the front cover. So, 4 of the authors on these two publications will be involved in teaching on the course. So we've got Kuan Torremans, John Walsh, myself and Peter Horton. We'll be bringing our very, very different interests to bear in common on this MSc. And I suppose, I mean, speaking personally, and I know this is true of other people as well, an MSc such as this one is a fantastic opportunity really to teach the stuff we research. So a lot of the undergraduate teaching we do, we're not really teaching the same stuff that we're doing the research in, because it's at a more fundamental level. But the opportunity to merge the teaching and the research and really teach what we're researching, because it's of relevance to industry, is very attractive to us. So, I've mentioned the minerals industry, I've mentioned the petroleum industry, I've mentioned that, a lot of the underlying approaches to modelling are the same, but of course they're also different. For example, the mineral industry typically relies on huge numbers of boreholes, but seismic data is pretty rare in the mineral industry, whereas the petroleum industry, of course, relies very, very strongly on 3D seismic data, and well data is much sparser. So in a way, the way the softwares have developed is a reflection of this. And, as I said, we're going to be using in this course these 2 packages, Leapfrog and Petrel, which are really some of the key softwares in these 2 industries. But, what we're dealing with isn't just related to industry. And this is an example of the Groninger gas field, one of the biggest gas fields in the world. Situated in the Netherlands. It's been producing gas since about 1960, I think. But in the last 15 years, they've really had to curb back on their gas production, in fact, stop it altogether a couple of years ago, because they've been inducing earthquakes. So there's been a tremendous amount of reservoir compaction and induced earthquakes due to gas production on this field, and really trying to understand the interactions of the subsurface geology, the geofluid extractions, the stress states, and the geomechanical controls on these earthquakes is a huge societal issue in this part of the Netherlands. We're on shore here. There are people living above this gas field. This is a bigger issue than simply resource management. This is really managing resources in a social, in a more, with more social relevance as well. So these geoscience, I suppose, and geomodeling are becoming more societal relevance in examples like this. And again, this is one of the examples we'll be looking at in the practical classes. Geological surveys, national geological surveys, increasingly are using geomodels rather than maps. I like to say that a three-dimensional geomodel is the new two-dimensional map. And these are just examples from the website of the Geological Survey of Ireland. Of course, we're in Ireland. And, they've still got a tremendous amount of mapping, of geological mapping, as the example on the left there. But increasingly, their website contains three-dimensional geomodels. And, geomodels are becoming, in a way, the default for national geological surveys. Someone's got to build these models. They're not straightforward to build, and a lot of the models you see built are, we need to be training people to understand how to build these models and to really build models successfully. Three-dimensional models are becoming increasingly important. So, our tagline is for a geoscience career in a changing world. And I've talked about how the world is changing because of increased volatility in job markets in geoscience sectors. But of course, one of the biggest changes in the world, of course, is climate change. And that's the one that we're all concerned about. That's the one that we all know about. And these pictorials here are basically summarizing CO2 emissions over the next 70 years according to the UN Sustainable Development Scenario. So according to this scenario, where we are now in 2020, we've got a huge amount of CO2 going into the atmosphere caused by burning fossil fuels. That's what that big orange arrow taking CO2 out of the ground and into the atmosphere is. By the time we get to 2050, 2070, there's a significant decline in the amount of carbon dioxide we expect to be taking out of the ground. According to the UN Sustainable Development Scenario, we're going to be changing our global energy mix. But of course, as geoscientists, we know that we're not going to be changing that global energy mix. We're not going to be moving away from hydrocarbons as quickly as we would perhaps, as many people perhaps think we should. Hydrocarbons are going to be with us for many years to come. There'll always be a need to or certainly for the foreseeable future, for the length of your careers, there will be a need to manage subsurface petroleum resources. But the other thing that this diagram is showing are the increasing arrows pointing into the ground. So there's the orange arrows, there's also a large green arrow by the time we get to 2070, and this is CO2 sequestration. So this is where we capture CO2 from industrial sources or from direct air capture in the blue arrows and store it permanently underground. So CO2 storage underground is a geoscience problem. It's a geomodeling problem. We need to tackle it using similar tools to the ones that we do to characterize hydrocarbon reservoirs. The other thing we should think about, of course, is, when we're talking about a move to other non-hydrocarbon related energy systems, is do we have the metals and other resources that we need to manage this change? And this matrix is showing the importance of different metals to clean energy, to renewable energy on going up, but also the risk to supply and the geological availability of different metals. So recognizing that the resources we need to move to clean energy also rely very much on availability of geological reserves that we need to manage, we need to explore, we need to extract. So yes, society is changing. We are moving to more sustainable energy resources, but that is still a geoscience problem. So part of what we're trying to address in this MSc is really managing some of these changes within a subsurface geoscience context. So that's our MSc in subsurface characterization and geomodeling. Really, we're trying to help you acquire the skills to manage and critically evaluate subsurface data. We're helping you learn to understand, model and visualize the subsurface using diverse data and methods, learn model transferable skills applicable across a range of geoscience sectors. We're looking at the traditional sectors, mineral resources, energy, including geothermal energy, groundwater, carbon sequestration, geotechnical services, national geological surveys, waste management. We're going to provide training in state-of-the-art industry software such as Petrel, Leapfrog, ArcGIS, but also in a range of soft skills, soft transferable skills like presenting, reporting, programming that are increasingly important, of course, for industry. And I've put at the bottom of this slide a recent photograph of, not that recent for obvious reasons, but a recent photograph of the School of Earth Sciences. And, that's kind of the size of the school. That includes the academic teaching staff. It also includes the postdoctoral research staff, and PhD students are in there as well. So we're a reasonably small, reasonably close group of people. And, we have a reasonably wide range of expertise that we're intending to bring to this MSc. The MSc itself, we've got individual workstations, dedicated teaching classrooms for the MSc within the UCD Science Centre on our South Dublin Parkland campus. And I just thought I'd finish up by briefly explaining the structure of the course. It's a full year, 1 year taught MSc class, and our teaching year is split into 3 different trimesters. So the first one runs from September to December and will largely consist of talk courses, lectures with individual practical sessions or small group practical classes, which, the assessment for that will largely be about 50-50 split between continual assessment and end of term examinations. The second semester is a bit more varied. We're still going to have many of these talk courses with small group and individual practical classes, but there's also some team-based competitive modelling exercises which are hard work, but they're also a bit of fun. And there's also a 2-week residential field class to the Pyrenees in the south of Spain, in the north of Spain, where we can really see many of the things we're teaching and pick up on a lot of the 3-dimensional visualization skills by really looking at the stuff in the field. And then the final trimester over the summer is an individual project, which is either done, within in-house within UCD, or often within a company. And that's really where you spread your wings a bit, I suppose, and apply some of the learnings from these things. It's a very important part of the whole MSc process, because it really proves that everyone is able to apply the skills they've learned and really come up with some good individual work. So that's me. That's the presentation I prepared for this session. I hope it's been of some use, and I'm very happy to answer any specific questions you might have on what I've presented, as well as, of course, more general questions that Antea and I can tackle about the MSc.